Before we can start graphing, we need to add. In order to add, we need a common denominator. Thankfully, we already have the common denominator. So I can go ahead and do the addition. Just adding the stuff, adding the like terms on the top. Now when I do that, I end up with a quadratic. And every time we see a quadratic, when we do one of these, I always want to see if I can factor it. And in this case, it does factor. The x squared minus 9x plus 20, notice factors to be x minus 5, x minus 4. All right, now that I have that, notice what that allows us to do. This simplifies, it reduces. Because what can I cancel out of both top and bottom?
X minus 5.
So I cancel out the x minus 5s, and notice I'm left with just x minus 4. Not 1 over x minus 4 because it was on the top, but just x minus 4. So that's actually the equation we're going to be working with here. We're going to be graphing y equals x minus 4 in a moment. But there is a little bit of nuance. We do need to still figure out what the restrictions would be. And so, what can x not equal?
5 and 4.
5, and only 5. Because remember that the restrictions are things that would have made the denominator equal 0, and only the denominator. The 4, it was in the numerator, so we don't care. It doesn't have to be a restriction. So, yes, this does equal this as long as x does not equal 5. And remember why? Because if x equaled 5 and I plugged it in up here, it would give me an answer of undefined. Whereas if I plug it in here, it would give me an answer of 1. So that's not equal in that one case. But every other way, no matter what we plug in for x, it would be the same. So then let's actually take a look at how we would make this graph then. What is our parent function going to be? Yeah, the parent function here is just y equals x. It's not 1 over x because it's not 1 over x minus 4. It's just x minus 4. And looking ahead, what does the graph of y equals x look like? It's a line, right? And so I know I'm going to be graphing a line here, but my line is being transformed specifically by this minus 4. What does the minus 4 do to the graph? It shifts it down 4, yes. And I treat it as down 4 because it's just hanging on the end there. There's not like parentheses connecting the x and the 4 or anything like that. All right, so it shifts it down 4. And then we always have been asking about the asymptotes recently, but in this case, there wouldn't be asymptotes. Remember, it's a line. It's not a reciprocal function, it's a line. But then I need to look and start seeing how would that graph look. So of course it's transformed by moving it down 4. So the very first thing I do is I plot a point that's down 4. And I'm going to go ahead and draw the parent function graph, y equals x, from that point. Well, it's a line, and the slope of my line is just 1, or in other words, I'm always going up 1 over 1, specifically up 1, right 1, because it's positive, all the way along that. Then once I've plotted those points, I can see where they are. I can draw the line in through those. And this is almost my graph, but not quite. This graph is not yet done. What is it missing? Yeah, the restrictions. We have to account for the fact that x did not equal 5. And so what that tells me to do is on my graph go over to where x equals 5, and instead of putting a point there like normal, I need to replace that with an empty circle. I got to put a hole in the graph to show where that comes up. And then having done that, we can then consider questions about domain and range. Domain. Well, if it was just the line without any hole in it, our domain would be all real numbers. Because it includes every possible x value. It's a line. It goes on forever. But the hole does change things a little bit. So our domain is actually going to be x does not equal 5. Yes. That's our restriction. It's exactly the same as what we found in our restrictions earlier. The domain is restrictions on the domain. They really are meaning the same thing. What we don't already have is the range. And so we actually have to figure out what that's going to be. And again, the range normally for this one would be all real numbers because it's going forever up and forever down. But we do have one y value that it doesn't actually reach. What is that y value that we don't actually hit? 1. Because we're looking at what is the y value of the whole. Or in other words, if I wanted to figure that out, and I couldn't quite tell just by looking at the graph like I can in this case, I could actually go back to my simplified equation, the y equals x minus 4 equation, and I could plug my 5 into that. So I could go y equals 5 minus 4, therefore y equaled 1. So that told me that when I plug in this 5, it looks like we should have a value at 1. Which is how I know where the hole is. Because it looks like there should be a value there, even though there really isn't. Hence why we have to know what the restrictions are through our algebraic work.